Chapter 5: Process Synchronization. A cooperating process is one that can affect or be affected by other processes executing in the system. Cooperating processes can either directly share a logical address space, that is, both code and data, or be allowed to share data only through files or messages. The former case is achieved through the use of threads. Concurrent access to shared data may result in data consistency, however. In this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space so that data consistency is maintained. Chapter Objectives: to introduce the critical section problem whose solutions can be used to ensure the consistency of shared data. To present both software and hardware solutions of the critical section problem. To examine several classical process synchronization problems. To explore several tools that are used to solve process synchronization problems. Background: we have already seen that processes can execute concurrently or in parallel. In Chapter 3, we introduced the role of process scheduling and described how the CPU scheduler switches rapidly between processes to provide concurrent execution. This means that one process may only partially complete execution before another process is scheduled. In fact, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instructions of another process. Additionally, Chapter 4 introduced parallel execution, in which two instruction streams representing different processes execute simultaneously on separate processing cores. In this chapter, we explain how concurrent or parallel execution can contribute to issues involving the integrity of data shared by several processes. Let's consider an example of how this can happen. In Chapter 3, we developed a model of a system consisting of cooperating sequential processes or threads, all running asynchronously and possibly sharing data. We illustrated this model with the producer-consumer problem, which is representative of operating systems. We also described how a bounded buffer could be used to enable processes to share memory. We now return to our consideration of the bounded buffer. As we pointed out, our original solution allowed at most buffer size minus 1 items in the buffer at the same time. Suppose we want to modify the algorithm to remedy this deficiency. One possibility is to add an integer variable counter initialized to 0. Counter is incremented every time we add a new item to the buffer and is decremented every time we remove one item from the buffer. The code for the producer process can be modified as given here. The code for the consumer process can be modified as given here. Although the producer and consumer routines shown here are correct separately, they may not function correctly when executed concurrently. As an illustration, suppose that the value of the variable counter is currently 5 and the producer and consumer processes concurrently execute the statements counter plus plus and counter minus minus. Following the execution of these two statements, the value of the variable counter may be 4, 5 or 6. The only correct result, though, is counter equal to 5, which is generated correctly if the producer and consumer execute separately. We can show that the value of the counter may be incorrect as given here. Note that the statement counter plus plus may be implemented in machine language on a typical machine as given here. Register 1 is equal to counter, register 1 is equal to register 1 plus 1, counter equal to register 1, where register 1 is one of the local CPU registers. Similarly, the statement counter minus minus is implemented as follows. Register 2 equal to counter, register 2 equal to register 2 minus 1, counter equal to register 2, where again register 2 is one of the local CPU registers. Even though register 1 and register 2 may be the same physical register and accumulator say, Remember that the contents of this register may be saved and restored by the interrupt handler. The concurrent execution of counter plus plus and counter minus minus is equivalent to a sequential execution in which the lower level statements presented previously are interleaved in some arbitrary order, but the order within each high level statement is preserved. One such interleaving is given here. Notice that we have arrived at the incorrect state counter equal to 4, indicating that 4 buffers are full when in fact 5 buffers are full. If we reversed the order of the statements S4 and S5, we would arrive at the incorrect state counter equal to 6. We would arrive at this incorrect state because we allowed both processes to manipulate the variable counter concurrently. A situation like this, where several processes access and manipulate the same data concurrently and the outcome of the execution depends on the particular order in which the access takes place, is called a race condition. To guard against the race condition above, we need to ensure that only one process at a time can be manipulating the variable counter. To make such a guarantee, we require that the processes be synchronized in some way. Situations such as the one described occur frequently in operating systems as different parts of the system manipulate resources. Furthermore, as we have emphasized in earlier chapters, the growing importance of multi-core systems has brought an increased emphasis on developing multi-threaded applications. In such applications, several threads which are quite possibly sharing data are running in parallel on different processing cores. Clearly, we want any changes that result from such activities not to interfere with one another. Because of the importance of this issue, we devote a major portion of this chapter to process synchronization and coordination among cooperating processes. The critical section problem. We begin our consideration of process synchronization by discussing the so-called critical section problem. Consider a system consisting of n processes P0, P1 up to Pn-1. Each process has a segment of code called a critical section, in which the process may be changing common variables, updating a table, writing a file, or so on. The important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. That is, no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. The critical section may be followed by an exit section. The remainder code is the remainder section. The general structure of a typical process PI is shown in this figure. The entry section and the exit section are enclosed in boxes to highlight these important segments of code. A solution to the critical section problem must satisfy the following three requirements. 1. Mutual exclusion. If process PI is executing in its critical section, then no other processes can be executing in their critical section. 2. Progress. If no process is executing in its critical section and some processes wish to enter their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which will enter its critical section next, and this selection cannot be postponed indefinitely. 3. Bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. We assume that each process is executing at a non-zero speed. However, we can make no assumption concerning the relative speed of the n processes. At a given point in time, many kernel mode processes may be active in the operating system. As a result, the code implementing an operating system, kernel code, is subject to several possible race conditions. Consider as an example a kernel data structure that maintains a list of all open files in the system. This list must be modified when a new file is opened or closed, adding the file to the list or removing it from the list. If two processes were to open files simultaneously, the separate updates to this list could result in a race condition. Other kernel data structures that are prone to possible race conditions include structures for maintaining memory allocation, for maintaining process lists, and for interrupt handling. It is up to kernel developers to ensure that the operating system is free from such race conditions. Two general approaches are used to handle critical sections in operating systems: preemptive kernels and non-preemptive kernels. A preemptive kernel allows a process to be preempted while it is running in kernel mode. A non-preemptive kernel does not allow a process running in kernel mode to be preempted. A kernel mode process will run until it exits kernel mode, blocks, or voluntarily yields control of the CPU. Obviously, a non-preemptive kernel is essentially free from race conditions on kernel data structures, as only one process is active in the kernel at a time. We cannot say the same about preemptive kernels, so they must be carefully designed to ensure that shared kernel data are free from race conditions. Preemptive kernels are especially difficult to design for SMP architectures, since in these environments it is possible for two kernel mode processes to run simultaneously on different processors. Why then would anyone favor a preemptive kernel over a non-preemptive one? A preemptive kernel may be more responsive since there is less risk that a kernel mode process will run for an arbitrarily long period before relinquishing the processor to waiting processes. Of course, this risk can also be minimized by designing kernel code that does not behave in this way. Furthermore, a preemptive kernel is more suitable for real-time programming, as it will allow a real-time process to preempt a process currently running in the kernel. Later in this chapter, we explore how various operating systems manage preemption within the kernel. This figure represents a generic algorithm for process Pi, which has a critical section. Peterson's solution. Next, we illustrate a classic software-based solution to the critical section problem known as Peterson's solution. Because of the way modern computer architectures perform basic machine language instructions such as load and store, there are no guarantees that Peterson's solution will work correctly on such architectures. However, we present the solution because it provides a good algorithmic description of solving the critical section problem and illustrates some of the complexities involved in designing software that addresses the requirements of mutual exclusion, progress, and bounded waiting. Peterson's solution is restricted to two processes that alternate execution between their critical sections and remainder sections. The processes are numbered P0 and P1. For convenience, when presenting Pi, we use Pj to denote the other processes, that is, j equals 1 minus I. So Peterson's solution requires the two processes to share two data items, int turn and boolean flag 2. The variable turn indicates whose turn it is to enter its critical section. That is, if turn is equal to I, then process Pi is allowed to execute in its critical section. The flag array is used to indicate if a process is ready to enter its critical section. For example, if flag I is true, this value indicates that Pi is ready to enter its critical section. With an explanation of these data structures complete, we are now ready to describe the algorithm. To enter the critical section, process Pi first sets flag I to be true and then sets turn to the value j, thereby asserting that if the other process wishes to enter the critical section, it can do so. If both the processes try to enter at the same time, turn will be set to both I and j at roughly the same time. Only one of these assignments will last. The other will occur but will be overwritten immediately. The eventual value of turn determines which of the two processes is allowed to enter its critical section first. We now prove that this solution is correct. We need to show that 1. Mutual exclusion is preserved, 2. The progress requirement is satisfied, 3. The bounded waiting requirement is met. To prove property 1, we note that each Pi enters its critical section only if either flag j is equal to false or turn is equal to I. Also note that if both processes can be executing in their critical sections at the same time, then flag 0 is equal to flag 1 is equal to true. These two observations imply that P0 and P1 could not have successfully executed their while statements at about the same time, since the value of turn can be either 0 or 1 but cannot be both. Hence, one of the processes, say Pj, must have successfully executed the while statement, whereas Pi had to execute at least one additional statement, turn is equal to j. However, at that time, flag j is equal to true and turn is equal to j, and this condition will persist as long as Pj is in its critical section. As a result, mutual exclusion is preserved. To prove properties 2 and 3, we note that a process Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition flag j is equal to true and turn j is equal to j. This loop is the only one possible. If Pj is not ready to enter the critical section, then flag j is equal to false and Pi can enter its critical section. If Pj has set flag j to true and is also executing in its while statement, then either turn is equal to I or turn is equal to j. If turn is equal to I, then Pi will enter the critical section. If turn is equal to j, then Pj will enter the critical section. However, once Pj exits its critical section, it will reset flag j to false, allowing Pi to enter its critical section. If Pj resets flag j to true, it must also set turn to I. Thus, since Pi does not change the value of the variable turn while executing the while statement, Pi will enter the critical section, progress, after at most only one entry by Pj, that is bounded waiting. Synchronization hardware. We have just described one software-based solution to the critical section problem. However, as mentioned, software-based solutions such as Peterson's are not guaranteed to work on modern computer architectures. In the following discussions, we explore several more solutions to the critical section problem using techniques ranging from hardware to software-based APIs available to both kernel developers and application programmers. All these solutions are based on the premise of locking, that is, protecting critical regions through the use of locks. As we shall see, the designs of such locks can be quite sophisticated. We start by presenting some simple hardware instructions that are available on many systems and showing how they can be used effectively in solving the critical section problem. Hardware features can make any programming task easier and improve system efficiency. The critical section problem could be solved simply in a single processor environment if we could prevent interrupts from occurring while a shared variable was being modified. In this way, we could be sure that the current sequence of instructions would be allowed to execute in order without preemption. No other instructions would be run, so no unexpected modifications could be made to the shared variable. This is often the approach taken by non-preemptive kernels. Unfortunately, this solution is not as feasible in a multiprocessor environment. Disabling interrupts on a multiprocessor can be time-consuming since the message is passed to all the processors. This message passing delays entry into each critical section, and system efficiency decreases. Also consider the effect on a system's clock if the clock is kept updated by interrupts. Many modern computer systems therefore provide special hardware instructions that allow us either to test and modify the content of a word or to swap the contents of two words atomically, that is, as one uninterruptible unit. We can use these special instructions to solve the critical section problem in a relatively simple manner. Rather than discussing one specific instruction for one specific machine, we abstract the main concepts behind these types of instructions by describing the test and set and compare and swap instructions. This figure represents the solution to critical section problem using locks. The test and set instruction can be defined as in the figure given here. The important characteristic of this instruction is that it is executed atomically. Thus, if two test and set instructions are executed simultaneously, each on a different CPU, they will be executed sequentially in some arbitrary order. If the machine supports the test and set instruction, then we can implement mutual exclusion by declaring a Boolean variable lock initialized to false. The structure of process PI is shown here. The compare and swap instruction, in contrast to the test and set instruction, operates on three operands. It is defined as shown here in the given figure. The operand value is set to new value only if the expression star value is equal to expected is true. Regardless, compare and swap always returns the original value of the variable value. Like the test and set instruction, compare and swap is executed atomically. Mutual exclusion can be provided as follows. A global variable lock is declared and is initialized to 0. The first process that invokes compare and swap will set lock to 1. It will then enter its critical section because the original value of lock was equal to the expected value of 0. Subsequent calls to compare and swap will not succeed because lock now is not equal to the expected value of 0. When a process exits its critical section, it sets lock back to 0, which allows another process to enter its critical section. The structure of process P is shown in the given figure. Although these algorithms satisfy the mutual exclusion requirement, they do not satisfy the bounded waiting requirement. In the given figure, we present another algorithm using the test and set instruction that satisfies all the critical section requirements. The common data structures are Boolean waiting n, Boolean lock. These data structures are initialized to false. To prove that the mutual exclusion requirement is met, we note that process Pi can enter its critical section only if either waiting I is equal to false or key is equal to false. The value of key can become false only if the test and set is executed. The first process to execute the test and set will find key is equal to false. All others must wait. The variable waiting I can become false only if another process leaves its critical section. Only one waiting I is set to false, maintaining the mutual exclusion requirement. To prove that the progress requirement is met, we note that the arguments presented for mutual exclusion also apply here. Since a process exiting the critical section either sets lock to false or sets waiting j to false, both allow a process that is waiting to enter its critical section to proceed. To prove that the bounded waiting requirement is met, we note that when a process leaves its critical section, it scans the array waiting in the cyclic ordering. I plus 1, I plus 2 goes to n minus 1, 0 goes to I minus 1. It designates the first process in this ordering that is in the entry section, waiting j is equal to true, as the next one to enter the critical section. Any process waiting to enter its critical section will thus do so within n minus 1 turns. Details describing the implementation of the atomic, test and set, and compare and swap instructions are discussed more fully in books on computer architecture. Mutex locks. The hardware-based solutions to the critical section problem presented earlier are complicated as well as generally inaccessible to application programmers. Instead, operating system designers build software tools to solve the critical section problem. The simplest of these tools is the mutex lock. In fact, the term mutex is short for mutual exclusion. We use the mutex lock to protect critical regions and thus prevent race conditions. That is, a process must acquire the lock before entering a critical section. It releases the lock when it exits the critical section. The acquire function acquires the lock and the release function releases the lock. A mutex lock has a Boolean variable available, whose value indicates if the lock is available or not. If the lock is available, a call to acquire succeeds and the lock is then considered unavailable. A process that attempts to acquire an unavailable lock is blocked until the lock is released. Calls to either acquire or release must be performed atomically. Thus, mutex locks are often implemented using one of the hardware mechanisms described earlier, and we leave the description of this technique as an exercise. The main disadvantage of the implementation given here is that it requires busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the call to acquire. In fact, this type of mutex lock is also called a spin lock because the process spins while waiting for the lock to become available. We see the same issue with the code examples illustrating the test and set instruction and the compare and swap instruction. This continual looping is clearly a problem in a real multi-programming system, where a single CPU is shared among many processes. Busy waiting wastes CPU cycles that some other process might be able to use productively. Spin locks do have an advantage, however, in that no context switch is required when a process must wait on a lock, and a context switch may take considerable time. Thus, when locks are expected to be held for short times, spin locks are useful. They are often employed on multiprocessor systems where one thread can spin on one processor while another thread performs its critical section on another processor. Later in this chapter, we examine how mutex locks can be used to solve classical synchronization problems. We also discuss how these locks are used in several operating systems as well as in pthreads. This figure shows the definition of acquire and release functions and also the solution to the critical section problem using mutex locks. Semaphores. Mutex locks, as we mentioned earlier, are considered the simplest of synchronization tools. In this section, we examine a more robust tool that can behave similarly to a mutex lock, but can also provide more sophisticated ways for processes to synchronize their activities. A semaphore S is an integer variable that, apart from initialization, is accessed only through two standard atomic operations, wait and signal. The wait operation was originally termed P, from the Dutch proberen, to test. Signal was originally called V, from verhogen, to increment. The definition of wait is given here. The definition of signal as well is given here. All modifications to the integer value of the semaphore in the wait and signal operations must be executed indivisibly. That is, when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. In addition, in the case of wait S, the testing of the integer value of S less than equal to 0, as well as its possible modification S minus minus, must be executed without interruption. We shall see how these operations can be implemented a little later. First, let's see how semaphores can be used. Semaphore usage. Operating systems often distinguish between counting and binary semaphores. The value of a counting semaphore can range over an unrestricted domain. The value of a binary semaphore can range only between 0 and 1. Thus, binary semaphores behave similarly to mutex locks. In fact, on systems that do not provide mutex locks, binary semaphores can be used instead for providing mutual exclusion. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. Each process that wishes to use a resource performs a wait operation on the semaphore, thereby decrementing the count. When a process releases a resource, it performs a signal operation, incrementing the count. When the count for the semaphore goes to 0, all the resources are being used. After that, processes that wish to use a resource will block until the count becomes greater than 0. We can also use semaphores to solve various synchronization problems. For example, consider two concurrently running processes, P1 with a statement S1 and P2 with a statement S2. Suppose we require that S2 be executed only after S1 has completed. We can implement this scheme readily by letting P1 and P2 share a common semaphore sync, initialized to 0. In process P1, we insert the statements given here, S1 and then signal sync. In process P2, we insert the statements as given here, wait, sync, S2. Because sync is initialized to 0, P2 will execute S2 only after P1 has invoked signal sync, which is after statement S1 has been executed. Semaphore implementation. Recall that the implementation of mutex locks discussed earlier suffers from busy waiting. The definitions of the wait and signal semaphore operations just described present the same problem. To overcome the need for busy waiting, we can modify the definitions of the wait and signal operations as follows. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process can block itself. The block operation places a process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting state. Then control is transferred to the CPU scheduler, which selects another process to execute. A process that is blocked waiting on a semaphore S should be restarted when some other process executes a signal operation. The process is restarted by a wake-up operation, which changes the process from the waiting state to the ready state. The process is then placed in the ready queue. The CPU may or may not be switched from the running process to the newly ready process, depending on the CPU scheduling algorithm. To implement semaphores under this definition, we define a semaphore as given here. Each semaphore has an integer value and a list of processes list. When a process must wait on a semaphore, it is added to the list of processes. A signal operation removes one process from the list of waiting processes and awakens that process. The definitions of wait and signal semaphore operations are given here. The block operation suspends the process that invokes it. The wake-up P operation resumes the execution of a blocked process P. These two operations are provided by the operating system as basic system calls. Note that in this implementation, semaphore values may be negative, whereas semaphore values are never negative under the classical definition of semaphores with busy waiting. If a semaphore value is negative, its magnitude is the number of processes waiting on that semaphore. This fact results from the switching the order of the decrement and the test in the implementation of the wait operation. The list of waiting processes can be easily implemented by a link field in each process control block PCB. Each semaphore contains an integer value and a pointer to a list of PCBs. One way to add and remove processes from the list so as to ensure bounded waiting is to use a FIFO queue, where the semaphore contains both head and tail pointers to the queue. In general, however, the list can use any queuing strategy. Correct usage of semaphores does not depend on a particular queuing strategy for the semaphore lists. It is critical that semaphore operations be executed atomically. We must guarantee that no two processes can execute wait and signal operations on the same semaphore at the same time. This is a critical section problem, and in a single processor environment, we can solve it by simply inhibiting interrupts during the time the wait and signal operations are executing. This scheme works in a single processor environment because once interrupts are inhibited, instructions from different processes cannot be interleaved. Only the currently running process executes until interrupts are re-enabled, and the scheduler can regain control. In a multiprocessor environment, interrupts must be disabled on every processor. Otherwise, Instructions from different processes running on different processors may be interleaved in some arbitrary way. Disabling interrupts on every processor can be a difficult task and furthermore can seriously diminish performance. Therefore, SMP systems must provide alternative locking techniques such as compare and swap or spin locks to ensure that wait and signals are performed atomically. It is important to admit that we have not completely eliminated busy waiting with this definition of the wait and signal operations. Rather, we have moved busy waiting from the entry section to the critical sections of application programs. Furthermore, we have limited busy waiting to the critical sections of the wait and signal operations, and these sections are short if properly coded. They should be no more than about 10 instructions. Thus, the critical section is almost never occupied and busy waiting occurs rarely, and then for only a short time. An entirely different situation exists with application programs whose critical sections may be long, minutes or even hours, or may almost always be occupied. In such cases, busy waiting is extremely inefficient. Deadlocks and starvation. The implementation of a semaphore with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. The event in question is the execution of a signal operation. When such a state is reached, these processes are said to be deadlocked. To illustrate this, consider a system consisting of two processes P0 and P1, each accessing two semaphores S and Q set to the value 1. Suppose that P0 executes wait S and then P1 executes wait Q. When P0 executes wait Q, it must wait until P1 executes signal Q. Similarly, when P1 executes wait S, it must wait until P0 executes signal S. Since these signal operations cannot be executed, P0 and P1 are deadlocked. We say that a set of processes is in a deadlocked state when every process in the set is waiting for an event that can be caused only by another process in the set. The events with which we are mainly concerned here are resource acquisition and release. Another problem related to deadlocks is indefinite blocking or starvation, a situation in which processes wait indefinitely within the semaphore. Indefinite blocking may occur if we remove processes from the list associated with a semaphore in LIFO, last in, first out order. Priority inversion. A scheduling challenge arises when a higher priority process needs to read or modify kernel data that are currently being accessed by a lower priority process or a chain of lower priority processes. Since kernel data are typically protected with a lock, the higher priority process will have to wait for a lower priority process to finish with the resource. The situation becomes more complicated if the lower priority process is preempted in favor of another process with a higher priority. As an example, assume we have three processes L, M and H whose priorities follow the order L less than M less than H. Assume that process H acquires resource R, which is currently being accessed by process L. Ordinarily, process H would wait for L to finish using resource R. However, now suppose that process M becomes runnable, thereby preempting process L, Indirectly, a process with a lower priority, process M, has affected how long process H must wait for L to relinquish resource R. This problem is known as priority inversion. It occurs only in systems with more than two priorities, so one solution is to have only two priorities. That is insufficient for most general purpose operating systems, however. Typically, these systems solve the problem by implementing a priority inheritance protocol. According to this protocol, all processes that are accessing resources needed by a higher priority process inherit the higher priority until they are finished with the resources in question. When they are finished, their priorities revert to their original values. In the example given here, a priority inheritance protocol would allow process L to temporarily inherit the priority of a process H, thereby preventing process M from preempting its execution. When process L had finished using resource R, it would relinquish its inherited priority from H and assume its original priority. Because resource R would now be available, process H, not M, would run next. Classic problems of synchronization. In this section, we present a number of synchronization problems as examples of a large class of concurrency control problems. These problems are used for testing nearly every newly proposed synchronization scheme. In our solutions to the problems, we used semaphores for synchronization since that is the traditional way to present such solutions. However, actual implementations of these solutions could use mutex locks in place of binary semaphores. The bounded buffer problem. The bounded buffer problem was introduced earlier. It is commonly used to illustrate the power of synchronization primitives. Here we present a general structure of this scheme without committing ourselves to any particular implementation. In our problem, the producer and consumer processes share the following data structures: int n, semaphore mutex equal to 1, semaphore empty equal to n, semaphore full equal to 0. We assume that the pool consists of n buffers, each capable of holding one item. The mutex semaphore provides mutual exclusion for accesses to the buffer pool and is initialized to the value 1. The empty and full semaphores count the number of empty and full buffers. The semaphore empty is initialized to the value n. The semaphore full is initialized to the value 0. The code for the producer process is shown here. The code for the consumer process is shown here. Note the symmetry between the producer and the consumer. We can interpret this code as the producer producing full buffers for the consumer, or as the consumer producing empty buffers for the producer. The readers-writers problem. Suppose that a database is to be shared among several concurrent processes. Some of these processes may want only to read the database, whereas others may want to update, that is, to read and write the database. We distinguish between these two types of processes by referring to the former as readers and to the latter as writers. Obviously, if two readers access the shared data simultaneously, no adverse effects take place. However, if a writer and some other process, either a reader or a writer, access the database simultaneously, chaos may ensue. To ensure that these difficulties do not arise, we require that the writers have exclusive access to the shared database while writing to the database. This synchronization problem is referred to as the readers-writers problem. Since it was originally stated, it has been used to test nearly every new synchronization primitive. The readers-writers problem has several variations, all involving priorities. The simplest one, referred to as the first readers-writers problem, requires that no reader be kept waiting unless a writer has already obtained permission to use the shared object. In other words, no reader should wait for other readers to finish simply because a writer is waiting. The second readers-writers problem requires that once a writer is ready, that writer perform its write as soon as possible. In other words, if a writer is waiting to access the object, no new readers may start reading. A solution to either problem may result in starvation. In the first case, writers may starve. In the second case, readers may starve. For this reason, other variants of the problem have been proposed. Next, we present a solution to the first readers-writers problem. In the solution to the first readers-writers problem, the reader processes share the following data structures: Semaphore RW mutex equal to 1, Semaphore mutex equal to 1, int read count equal to 0. The Semaphores mutex and RW mutex are initialized to 1. Read count is initialized to 0. The Semaphore RW mutex is common to both reader and writer processes. The mutex semaphore is used to ensure mutual exclusion when the variable read count is updated. The read count variable keeps track of how many processes are currently reading the object. The Semaphore RW mutex functions as a mutual exclusion semaphore for the writers. It is also used by the first or last reader that enters or exits the critical section. It is not used by readers who enter or exit while other readers are in their critical sections. The code for a writer process and a reader process is shown here. Note that if a writer is in the critical section and n readers are waiting, then one reader is queued on RW mutex and n-1 readers are queued on mutex. Also observe that when a writer executes signal RW mutex, we may resume the execution of either the waiting readers or a single waiting writer. The selection is made by the scheduler. The readers-writers problem and its solutions have been generalized to provide reader-writer locks on some systems. Acquiring a reader-writer lock requires specifying the mode of the lock, either read or write access. When a process wishes only to read shared data, it requests the reader-writer lock in read mode. A process wishing to modify the shared data must request the lock in write mode. Multiple processes are permitted to concurrently acquire a reader-writer lock in read mode, but only one process may acquire the lock for writing, as exclusive access is required for writers. Reader-writer locks are most useful in the following situations. In applications where it is easy to identify which processes only read shared data and which processes only write shared data. In applications that have more readers than writers. This is because reader-writer locks generally require more overhead to establish than semaphores or mutual exclusion locks. The increased concurrency of allowing multiple readers compensates for the overhead involved in setting up the reader-writer lock. The dining philosopher's problem. Consider 5 philosophers who spent their lives thinking and eating. The philosophers share a circular table surrounded by 5 chairs, each belonging to one philosopher. In the center of the table is a bowl of rice, and the table is laid with 5 single chopsticks. When a philosopher thinks, she does not interact with her colleagues. From time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks that are closest to her. The chopsticks that are between her and her left and right neighbors. A philosopher may pick up only one chopstick at a time. Obviously, she cannot pick up a chopstick that is already in the hand of a neighbor. When a hungry philosopher has both her chopsticks at the same time, she eats without releasing the chopsticks. When she is finished eating, she puts down her chopsticks and starts thinking again. The dining philosopher's problem is considered a classic synchronization problem, neither because of its practical importance nor because computer scientists dislike philosophers, but because it is an example of a large class of concurrency control problems. It is a simple representation of the need to allocate several resources among several processes in a deadlock-free and starvation-free manner. One simple solution is to represent each chopstick with a semaphore. A philosopher tries to grab a chopstick by executing a wait operation on that semaphore. She releases her chopsticks by executing the signal operation on the appropriate semaphores. Thus, the shared data are semaphore chopstick 5, where all the elements of chopstick are initialized to 1. The structure of the philosopher I is shown here. Although this solution guarantees no 2 neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. Suppose that all 5 philosophers become hungry at the same time, and each grabs her left chopstick. All the elements of chopstick will now be equal to 0. When each philosopher tries to grab her right chopstick, she will be delayed forever. Several possible remedies to the deadlock problem are replaced by allow at most 4 philosophers to be sitting simultaneously at the table. Allow a philosopher to pick up her chopsticks only if both chopsticks are available. To do this, she must pick them up in a critical section. Use an asymmetric solution, that is, an odd-numbered philosopher picks up her first chopstick and then her right chopstick, whereas an even-numbered philosopher picks up her right chopstick and then her left chopstick. In the next section, we present a solution to the dining philosopher's problem that ensures freedom from deadlocks. Note, however, that any satisfactory solution to the dining philosopher's problem must guard against the possibility that one of the philosophers will starve to death. Deadlock solution does not necessarily eliminate the possibility of starvation. Although semaphores provide a convenient and effective mechanism for process synchronization, using them incorrectly can result in timing errors that are difficult to detect. Since these errors happen only if particular execution sequences take place, and these sequences do not always occur. We have seen an example of such errors in the use of counters in our solution to the producer-consumer problem. In that example, the timing problem happened only rarely, and even then the counter value appeared to be reasonable, off by only 1. Nevertheless, the solution is obviously not an acceptable one. It is for this reason that semaphores were introduced in the first place. Unfortunately, such timing errors can still occur when semaphores are used. To illustrate how, we review the semaphore solution to the critical section problem. All processes share a semaphore variable mutex, which is initialized to 1. Each process must execute wait mutex before entering the critical section and signal mutex afterward. If this sequence is not observed, two processes may be in their critical sections simultaneously. Next, we examine the various difficulties that may result. Note that these difficulties will arise even if a single process is not well behaved. This situation may be caused by an honest programming error or an uncooperative programmer. Suppose that a process interchanges the order in which the wait and signal operations on the semaphore mutex are executed, resulting in the following execution: signal mutex, critical section, and then wait mutex. In this situation, several processes may be executing in their critical sections simultaneously, violating the mutual exclusion requirement. This error may be discovered only if several processes are simultaneously active in their critical sections. Note that this situation may not always be reproducible. Suppose that a process replaces signal mutex with wait mutex. That is, it executes wait mutex, critical section, wait mutex. In this case, a deadlock will occur. Suppose that a process omits the wait mutex or the signal mutex, or both. In this case, either mutual exclusion is violated or a deadlock will occur. These examples illustrate that various types of errors can be generated easily when programmers use semaphores incorrectly to solve the critical section problem. Similar problems may arise in the other synchronization models discussed later. To deal with such errors, researchers have developed high-level language constructs. In this section, we describe one fundamental high-level synchronization construct, the monitor type. Monitor usage. An abstract data type, or ADT, encapsulates data with a set of functions to operate on that data that are independent of any specific implementation of the ADT. A monitor type is an ADT that includes a set of programmer-defined operations that are provided with mutual exclusion within the monitor. The monitor type also declares the variables whose values define the state of an instance of that type, along with the bodies of functions that operate on those variables. The syntax of a monitor type is shown here. The representation of a monitor type cannot be used directly by the various processes. Thus, a function defined within a monitor can access only those variables declared locally within the monitor and its formal parameters. Similarly, the local variables of a monitor can be accessed by only the local functions. The monitor construct ensures that only one process at a time is active within the monitor. Consequently, the programmer does not need to code this synchronization constraint explicitly. However, the monitor construct as defined so far is not sufficiently powerful for modeling some synchronization schemes. For this purpose, we need to define additional synchronization mechanisms. These mechanisms are provided by the condition construct, which we will discuss next. This is a schematic view of a monitor. A programmer who needs to write a tailor-made synchronization scheme can define one or more variables of type condition x, y. The only operations that can be invoked on a condition variable are wait and signal. The operation x.wait means that the process invoking this operation is suspended until another process invokes x.signal. The x.signal operation resumes exactly one suspended process. If no process is suspended, then the signal operation has no effect. That is, the state of x is the same as if the operation had never been executed. Contrast this operation with the signal operation associated with semaphores, which always affects the state of the semaphore. This represents the monitor with condition variables. Now suppose that when the x.signal operation is invoked by a process P, there exists a suspended process Q associated with condition X. Clearly, if the suspended process Q is allowed to resume its execution, the signaling process P must wait. Otherwise, both P and Q would be active simultaneously within the monitor. Note, however, that conceptually both processes can continue with their execution. Two possibilities exist. 1. Signal and wait. P either waits until Q leaves the monitor or waits for another condition. 2. Signal and continue. Q either waits until P leaves the monitor or waits for another condition. There are reasonable arguments in favor of adopting either option. On the one hand, since P was already executing in the monitor, the signal and continue method seems more reasonable. On the other, if we allow thread P to continue, then by the time Q is resumed, the logical condition for which Q was waiting may not hold anymore. A compromise between these two choices was adopted in the language concurrent Pascal. When thread P executes the signal operation, it immediately leaves the monitor. Hence, Q is immediately resumed. Many programming languages have incorporated the idea of the monitor as described here, including Java and C#. Other languages such as Erlang provide some type of concurrency support using a similar mechanism. Next, we illustrate monitor concepts by presenting a deadlock-free solution to the dining philosopher's problem. This solution imposes the restriction that a philosopher may pick up her chopsticks only if both of them are available. To code this solution, we need to distinguish among three states in which we may find a philosopher. For this purpose, we introduce the following data structure. Enum, thinking, hungry, eating, state 5. Philosopher I can set the variable state I equal to eating only if her two neighbors are not eating. That is, state I plus 4 mod 5 is not equal to eating and state I plus 1 mod 5 is not equal to eating. We also declare another variable, condition self 5. This allows philosopher I to delay herself when she is hungry but is unable to obtain the chopsticks she needs. We are now in a position to describe our solution to the dining philosopher's problem. The distribution of the chopsticks is controlled by the monitor dining philosophers, whose definition is given here. Each philosopher, before starting to eat, must invoke the operation pickup. This act may result in the suspension of the philosopher process. After the successful completion of the operation, the philosopher may eat. Following this, the philosopher invokes the put down operation. Thus, philosopher I must invoke the operations pickup and put down in the following sequence. Dining philosophers dot pickup I, eat, dining philosophers dot put down I. It is easy to show that this solution ensures that no two neighbors are eating simultaneously and that no deadlocks will occur. We note, however, that it is possible for a philosopher to starve to death. We do not present a solution to this problem, but rather leave it as an exercise for you. Implementing a monitor using semaphores. We now consider a possible implementation of the monitor mechanism using semaphores. For each monitor, a semaphore mutex initialized to 1 is provided. A process must execute wait mutex before entering the monitor and must execute signal mutex after leaving the monitor. Since a signaling process must wait until the resumed process either leaves or waits, an additional semaphore next is introduced, initialized to 0. The signaling processes can use next to suspend themselves. An integer variable next count is also provided to count the number of processes suspended on next. Thus, each external function f is replaced by the given code. Mutual exclusion within a monitor is ensured. We can now describe how condition variables are implemented as well. For each condition x, we introduce a semaphore xSem and an integer variable xCount, both initialized to 0. The operation x.wait can now be implemented as given here. The operation x.signal can be implemented as given here. This implementation is applicable to the definitions of monitors given by both Hoare and Brinch-Hansen. In some cases, however, the generality of implementation is unnecessary, and a significant improvement in efficiency is possible. Resuming processes within a monitor. We turn now to the subject of process resumption order within a monitor. If several processes are suspended on condition X and an X.signal operation is executed by some process, then how do we determine which of the suspended processes should be resumed next? One simple solution is to use a first come, first served FCFS ordering, so that the process that has been waiting the longest is resumed first. In many circumstances, however, such a simple scheduling scheme is not adequate. For this purpose, the conditional wait construct can be used. This construct has the form x.waitC, where C is an integer expression that is evaluated when the wait operation is executed. The value of C, which is called a priority number, is then stored with the name of the process that is suspended. When x.signal is executed, the process with the smallest priority number is resumed next. To illustrate this new mechanism, consider the resource allocator monitor shown in this figure, which controls the allocation of a single resource among competing processes. Each process, when requesting an allocation of this resource, specifies the maximum time it plans to use the resource. The monitor allocates the resource to the process that has the shortest time allocation request. A process that needs to access the resource in question must observe the following sequence: r.acquire_t, access the resource, and then r.release. When R is an instance of type resource allocator, unfortunately, the monitor concept cannot guarantee that the preceding access sequence will be observed. In particular, the following problems can occur. A process might access a resource without first gaining access permission to the resource. A process might never release a resource once it has granted access to the resource. A process might attempt to release a resource that it never requested. A process might request the same resource twice without first releasing the resource. The same difficulties are encountered with the use of semaphores, and these difficulties are similar in nature to those that encouraged us to develop the monitor constructs in the first place. Previously, we had to worry about the correct use of semaphores. Now we have to worry about the correct use of higher level programmer definition operations, with which the compiler can no longer assist us. One possible solution to the current problem is to include the resource access operations within the resource allocator monitor. However, using this solution will mean that scheduling is done according to the built-in monitor scheduling algorithm rather than the one we have coded. To ensure that the processes observe the appropriate sequences, we must inspect all the programs that make use of the resource allocator monitor and its managed resource. We must check two conditions to establish the correctness of this system. First, user processes must always make their calls on the monitor in a correct sequence. Second, we must be sure that an uncooperative process does not simply ignore the mutual exclusion gateway provided by the monitor and try to access the shared resource directly without using the access protocols. Only if these two conditions can be ensured can we guarantee that no time-dependent errors will occur and that the scheduling algorithm will not be defeated. Although this inspection may be possible for a small static system, it is not reasonable for a large system or a dynamic system. This access control problem can be solved only through the use of additional mechanisms that are described later in chapter 14. Synchronization examples. We next describe the synchronization mechanisms provided by the Windows, Linux, and Solaris operating systems, as well as the pthreads API. We have chosen these three operating systems because they provide good examples of different approaches to synchronizing the kernel, and we have included the pthreads API because it is widely used for thread creation and synchronization by developers on Unix and Linux systems. As you will see in this section, the synchronization methods available in these differing systems vary in subtle and significant ways. Synchronization examples. We next describe the synchronization mechanisms provided by the Windows, Linux, and Solaris operating systems, as well as the pthreads API. We have chosen these three operating systems because they provide good examples of different approaches to synchronizing the kernel, and we have included the pthreads API because it is widely used for thread creation and synchronization by developers on Unix and Linux systems. As you will see in this section, the synchronization methods available in these differing systems vary in subtle and significant ways. Synchronization in Windows. The Windows operating system is a multi-threaded kernel that provides support for real-time applications and multiple processors. When the Windows kernel accesses a global resource on a single processor system, it temporarily masks interrupts for all interrupt handlers that may also access the global resource. On a multiprocessor system, Windows protects access to global resources using spin locks, although the kernel uses spin locks only to protect short code segments. Furthermore, for reasons of efficiency, the kernel ensures that a thread will never be preempted while holding a spin lock. For thread synchronization outside the kernel, Windows provides dispatcher objects. Using a dispatcher object, threads synchronize according to several different mechanisms, including mutex locks, semaphores, events, and timers. The system protects shared data by requiring a thread to gain ownership of a mutex, to access the data, and to release ownership when it is finished. Semaphores behave as we described earlier. Events are similar to condition variables, that is, they notify a waiting thread when a desired condition occurs. Finally, timers are used to notify one or more than one thread that a specified amount of time has expired. Dispatcher objects may be in either a signaled state or a non-signaled state. An object in a signaled state is available and a thread will not block when acquiring the object. An object in a non-signaled state is not available and a thread will block when attempting to acquire the object. A relationship exists between the state of a dispatcher object and the state of a thread. When a thread blocks on a non-signaled dispatcher object, its state changes from ready to waiting, and the thread is placed in a waiting queue for that object. When the state for the dispatcher object moves to signaled, the kernel checks whether any threads are waiting on the object. If so, the kernel moves one thread or possibly more from the waiting state to the ready state, where they can resume executing. The number of threads the kernel selects from the waiting queue depends on the type of the dispatcher object for which it is waiting. The kernel will select only one thread from the waiting queue for a mutex, since a mutex object may be owned by only a single thread. For an event object, the kernel will select all threads that are waiting for the event. We can use a mutex lock as an illustration of dispatcher objects and thread states. If a thread tries to acquire a mutex dispatcher object that is in a non-signaled state, that thread will be suspended and placed in a waiting queue for the mutex object. When the mutex moves to the signaled state because another thread has released the lock on the mutex, the thread waiting at the front of the queue will be moved from the waiting state to the ready state and will acquire the mutex lock. A critical section object is a user mode mutex that can often be acquired and released without kernel intervention. On a multiprocessor system, a critical section object first uses a spin lock while waiting for the other thread to release the object. If it spins too long, the acquiring thread will then allocate a kernel mutex and yield its CPU. Critical section objects are particularly efficient because the kernel mutex is allocated only when there is contention for the object. In practice, there is very little contention, so the savings are significant. Synchronization in Linux. Prior to version 2.6, Linux was a non-preemptive kernel, meaning that a process running in kernel mode could not be preempted, even if a higher priority process became available to run. Now, however, the Linux kernel is fully preemptive, so a task can be preempted when it is running in the kernel. Linux provides several different mechanisms for synchronization in the kernel, as most computer architectures provide instructions for atomic versions of simple math operations. The simplest synchronization technique within the Linux kernel is an atomic integer. which is represented using the opaque data type atomic T. As the name implies, all math operations using atomic integers are performed without interruption. Atomic integers are particularly efficient in situations where an integer variable, such as a counter, needs to be updated, since atomic operations do not require the overhead of locking mechanisms. However, their usage is limited to these sorts of scenarios. In situations where there are several variables contributing to a possible race condition, more sophisticated locking tools must be used. Mutex locks are available in Linux for protecting critical sections within the kernel. Here, a task must invoke the mutex lock function prior to entering a critical section and the mutex unlock function after exiting the critical section. If the mutex lock is unavailable, a task calling mutex lock is put into a sleep state and is awakened when the lock's owner invokes mutex unlock. Linux also provides spin locks and semaphores, as well as reader-writer versions of these two locks for locking in the kernel. On SMP machines, the fundamental locking mechanism is a spin lock, and the kernel is designed so that the spin lock is held only for short durations. On single processor machines, such as embedded systems with only a single processing core, spin locks are inappropriate for use and are replaced by enabling and disabling kernel preemption. That is, on a single processor system, rather than holding a spin lock, the kernel disables kernel preemption, and rather than releasing the spin lock, it enables kernel preemption. Linux uses an interesting approach to disable and enable kernel preemption. It provides two simple system calls: preempt disable and preempt enable for disabling and enabling kernel preemption. The kernel is not preemptible, however, if a task running in the kernel is holding a lock. To enforce this rule, each task in the system has a thread info structure containing a counter preempt count to indicate the number of locks being held by the task. When a lock is acquired, preempt count is incremented. It is decremented when a lock is released. If the value of preempt count for the task currently running in the kernel is greater than 0, it is not safe to preempt the kernel, as this task currently holds a lock. If the count is 0, the kernel can safely be interrupted, assuming that there are no outstanding calls to preempt disable. Spin locks, along with enabling and disabling kernel preemption, are used in the kernel only when a lock or disabling kernel preemption is held for a short duration. When a lock must be held for a longer period, semaphores or mutex locks are appropriate for use. Synchronization in Solaris. To control access to critical sections, Solaris provides adaptive mutex locks, condition variables, semaphores, reader-writer locks, and turnstiles. Solaris implements semaphores and condition variables essentially as they are presented earlier. In this section, we describe adaptive mutex locks, reader-writer locks, and turnstiles. An adaptive mutex protects access to every critical data item. On a multiprocessor system, an adaptive mutex starts as a standard semaphore implemented as a spin lock. If the data are locked and therefore already in use, the adaptive mutex does one of the two things. If the lock is held by a thread that is currently running on another CPU, the thread spins while waiting for the lock to become available, because the thread holding the lock is likely to finish soon. If the thread holding the lock is not currently in run state, the thread blocks, going to sleep until it is awakened by the release of the lock. It is put to sleep so that it will not spin while waiting, since the lock will not be freed very soon. A lock held by a sleeping thread is likely to be in this category. On a single processor system, the thread holding the lock is never running if the lock is being tested by another thread, because only one thread can run at a time. Therefore, on this type of system, threads always sleep rather than spin if they encounter a lock. Solaris uses the adaptive mutex method to protect only data that are accessed by short code segments. That is, a mutex is used if a lock will be held for less than a few hundred instructions. If the code segment is longer than that, the spin waiting method is exceedingly inefficient. For these longer code segments, condition variables and semaphores are used. If the desired lock is already held, the thread issues a wait and sleeps. When a thread frees the lock, it issues a signal to the next sleeping thread in the queue. The extra cost of putting a thread to sleep and waking it, and of the associated context switches, is less than the cost of wasting several hundred instructions waiting in a spin lock. Reader-writer locks are used to protect data that are accessed frequently but are usually accessed in a read-only manner. In these circumstances, reader-writer locks are more efficient than semaphores because multiple threads can read data concurrently, whereas semaphores always serialize access to the data. Reader-writer locks are relatively expensive to implement, so again, they are used only on long sections of code. Solaris uses turnstiles to order the list of threads waiting to acquire either an adaptive mutex or a reader-writer lock. A turnstile is a queue structure containing threads blocked on a lock. For example, if one thread currently owns the lock for a synchronized object, all other threads trying to acquire the lock will block and enter the turnstile for that lock. When the lock is released, the kernel selects a thread from the turnstile as the next owner of the lock. Each synchronized object with at least one thread blocked on the object's lock requires a separate turnstile. However, rather than associating a turnstile with each synchronized object, Solaris gives each kernel thread its own turnstile. Because a thread can be blocked only on one object at a time, this is more efficient than having a turnstile for each object. The turnstile for the first thread to block on a synchronized object becomes the turnstile for the object itself. Threads subsequently blocking on the lock will be added to this turnstile. When the initial thread ultimately releases the lock, it gains a new turnstile from a list of free turnstiles maintained by the kernel. To prevent a priority inversion, turnstiles are organized according to a priority inheritance protocol. This means that if a lower priority thread currently holds a lock on which a higher priority thread is blocked, the thread with the lower priority will temporarily inherit the priority of the higher priority thread. Upon releasing the lock, the thread will revert to its original priority. Note that the locking mechanisms used by the kernel are implemented for user-level threads as well. So the same types of locks are available inside and outside the kernel. A crucial implementation difference is the priority inheritance protocol. Kernel locking routines adhere to the kernel priority inheritance methods used by the scheduler. User-level thread locking mechanisms do not provide this functionality. To optimize Solaris performance, developers will have defined and refined and fine-tuned the locking methods. Because locks are used frequently and typically are used for crucial kernel functions, tuning their implementation and use can produce great performance gains. Earlier, we described the classical wait and signal semaphore operations. Pthreads names these operations semWait and semPost respectively. Just like mutex locks, all semaphore functions return 0 when successful and non-zero when an error condition occurs. There are other extensions to the pthreads API, including spin locks, but it is important to note that not all extensions are considered portable from one implementation to another. Alternative approaches. With the emergence of multi-core systems has come increased pressure to develop multi-threaded applications that take advantage of multiprocessing cores. However, multi-threaded applications present an increased risk of race conditions and deadlocks. Traditionally, techniques such as mutex locks, semaphores, and monitors have been used to address these issues, but as the number of processing cores increases, it becomes increasingly difficult to design multi-threaded applications that are free from race conditions and deadlocks. In this section, we explore various features provided in both programming languages and hardware that support designing thread-safe concurrent applications. Transactional memory. Quite often in computer science, ideas from one area of study can be used to solve problems in other areas. The concept of transactional memory originated in database theory, for example, yet it provides a strategy for process synchronization. A memory transaction is a sequence of memory read-write operations that are atomic. If all operations in a transaction are completed, the memory transaction is committed. Otherwise, the operations must be aborted and rolled back. The benefits of transactional memory can be obtained through features added to a programming language. Consider an example. Suppose we have a function update that modifies shared data. Traditionally, this function would be written using mutex locks or semaphores. However, using synchronization mechanisms such as mutex locks and semaphores involves many potential problems, including deadlock. Additionally, as the number of threads increases, traditional locking scales less well because the level of contention among threads for lock ownership becomes very high. As an alternative to traditional locking methods, new features that take advantage of transactional memory can be added to a programming language. In our example, suppose we add the construct atomic S, which ensures that the operations in S execute as a transaction. The advantage of using such a mechanism rather than locks is that the transactional memory system, not the developer, is responsible for guaranteeing atomicity. Additionally, because no locks are involved, deadlock is not possible. Furthermore, a transactional memory system can identify which statements in atomic blocks can be executed concurrently, such as concurrent read access to a shared variable. It is of course possible for a programmer to identify these situations and use reader-writer locks, but the task becomes increasingly difficult as the number of threads within an application grows. Transactional memory can be implemented in either software or hardware. Software transactional memory, STM as the name suggests, implements transactional memory exclusively in software. No special hardware is needed. STM works by inserting instrumentation code inside transaction blocks. The code is inserted by a compiler and manages each transaction by examining where statements may run concurrently and where specific low-level blocking is required. Hardware Transactional Memory (HTM) uses hardware cache hierarchies and cache coherency protocols to manage and resolve conflicts involving shared data residing in separate processes' caches. HTM requires no special code instrumentation and thus has less overhead than STM. However, HTM does require that existing cache hierarchies and cache coherency protocols be modified to support transactional memory. Transactional memory has existed for several years without widespread implementation. However, the growth of multi-core systems and the associated emphasis on concurrent and parallel programming have prompted a significant amount of research in this area on the part of both academics and commercial software and hardware vendors. OpenMP. In the previous chapter, we provided an overview of OpenMP and its support of parallel programming in a shared memory environment. Recall that OpenMP includes a set of compiler directives and an API. Any code following the compiler directive #pragma omp parallel is defined as a parallel region and is performed by a number of threads equal to the number of processing cores in the system. The advantage of OpenMP and similar tools is that thread creation and management are handled by the OpenMP library and are not the responsibility of application developers. Along with its #pragma omp parallel compiler directive, OpenMP provides the compiler directive #pragma omp critical, which specifies the code region following the directive as a critical section in which only one thread may be active at a time. In this way, OpenMP provides support for ensuring that threads do not generate race conditions. As an example of the use of the critical section compiler directive, first assume that the shared variable count can be modified in the update function. If the update function can be part of or invoked from a parallel region, a race condition is possible on the variable counter. The critical section compiler directive can be used to remedy this race condition and is coded as given here. The critical section compiler directive behaves much like a binary semaphore or mutex lock, ensuring that only one thread at a time is active in the critical section. If a thread attempts to enter a critical section when another thread is currently active in that section, that is, owns the section, the calling thread is blocked until the owner exits. If multiple critical sections must be used, each critical section can be assigned a separate name, and a rule can specify that no more than one thread may be active in a critical section of the same name simultaneously. An advantage of using the critical section compiler directive in OpenMP is that it is generally considered easier to use than standard mutex locks. However, a disadvantage is that application developers must still identify possible race conditions and adequately protect shared data using the compiler directive. Additionally, because the critical section compiler directive behaves much like a mutex lock, deadlock is still possible when two or more critical sections are identified. Functional programming languages. Most well-known programming languages such as C, C++, Java, and C# are known as imperative or procedural languages. Imperative languages are used for implementing algorithms that are state-based. In these languages, the flow of the algorithm is crucial to its correct operation, and state is represented with variables and other data structures. Of course, program state is mutable as variables may be assigned different values over time.
With the current emphasis on concurrent and parallel programming for multi-core systems, there has been greater focus on functional programming languages, which follow a programming paradigm much different from that offered by imperative languages. The fundamental difference between imperative and functional languages is that functional languages do not maintain state. That is, once a variable has been defined and assigned a value, its value is immutable, it cannot change. Because functional languages disallow mutable state, they need not be concerned with issues such as race conditions and deadlocks. Essentially, most of the problems addressed in this chapter are non-existent in functional languages. Several functional languages are presently in use, and we briefly mention two of them here, Erlang and Scala. The Erlang language has gained significant attention because of its support for concurrency and the ease with which it can be used to develop applications that run on parallel systems. Scala is a functional language that is also object-oriented. In fact, much of the syntax of Scala is similar to the popular object-oriented languages Java and C#. To summarize, given a collection of cooperating sequential processes that share data, mutual exclusion must be provided to ensure that a critical section of code is used by only one process or thread at a time. Typically, computer hardware provides several operations that ensure mutual exclusion. However, such hardware-based solutions are too complicated for most developers to use. Mutex locks and semaphores overcome this obstacle. Both tools can be used to solve various synchronization problems and can be implemented efficiently, especially if hardware support for atomic operations is available. Various synchronization problems, such as the bounded buffer problem, the readers-writers problem, and the dining philosophers problem, are important, mainly because they are examples of a large class of concurrency control problems. These problems are used to test nearly every newly proposed synchronization scheme. The operating system must provide the means to guard against timing errors, and several language constructs have been proposed to deal with these problems. Monitors provide a synchronization mechanism for sharing abstract data types. A condition variable provides a method by which a monitor function can block its execution until it is signaled to continue. Operating systems also provide support for synchronization. For example, Windows, Linux, and Solaris provide mechanisms such as semaphores, mutex locks, spin locks, and conditional variables to control access to shared data. The pthreads API provides support for mutex locks and semaphores, as well as condition variables. Several alternative approaches focus on synchronization for multi-core systems. One approach uses transactional memory, which may address synchronization issues using either software or hardware techniques. Another approach uses the compiler extensions offered by OpenMP. Finally, functional programming languages address synchronization issues by disallowing mutability.